Hello friends. How to implementing a system that manages IoT devices with a combination of pods and fog/cloud computing, along with neural networks for intrusion detection systems, IDs, protection, load prediction, and energy efficiency. Requires a comprehensive approach. Aman Shariarianaya.
Hello friends, in this tutorial we learn how to implementation a system that manages IoT device with a combination of pods and fog cloud computing along with neural network for intrusion detection system protection, load prediction and energy efficiency. Require a comprehensive approach. For implementation, comprehensive approach, prerequisites, tools, microKITs. First, install microKITs because a lightweight Kubernetes distribution to simulate the edge IoT environment. For install microKITs, use command snap install microKITs with option classic, and next with command microKITs status ready, and with microKITs enable add-ons, for example DNS. Next, kubectl. Install a kubectl to interact with the microKITs cluster. And Docker for building Docker image for IoT simulation, and fog nodes and IDS application, and Python and machine learning library for install Python with library like TensorFlow or PyTorch for developing the IDS neural network model, and Lens for download and install Lens for Kubernetes cluster visualization and management. For implementation this scenario, step 1, define IoT management architecture, IoT service for simulate IoT devices, generate data that is sent to fog nodes and fog layer. For fog nodes, perform initial data processing, basic load balancing and IDS check, and cloud layer use for handles comprehensive IDS processing using a neural network and load prediction for optimized resource management, and use neural network IDS for IDS with a neural network that provides anomaly detection, load balancing and energy efficiency distribution of resources. Step 2, set up namespace in microKITs. Create a separate namespaces to logically organize IoT device simulation, fog nodes, and cloud resources. With these 3 commands, with microKITs and kubectl, create namespace, IoT device, fog nodes, and cloud namespace. Step 3, deploy IoT device simulation. Set up Docker containers that simulate IoT device sending data to fog nodes through an MQTT broker. Create a Docker image for IoT simulation With this script, you can create Docker image, and for implement IoT simulate.py file with code to generate and publish data to the MQTT broker, build and push the Docker image to Docker Hub or your local registry. For use Docker Hub, you can create account in Docker Hub, deploy IoT simulators in Kubernetes. With this code, you can deploy simulators in Kubernetes, and next apply the deployment with this micro-K8s kubectl apply IoT simulator YAML file. And step 4, set up a fog nodes with basic IDS and load balancing. For this setup, deploy MQTT broker to receive data from IoT device. With this code, and after create this code, deploy fog nodes with basic IDS functionality with this script, deploy fog nodes with basic IDS functionality, and apply the configuration MQTT broker and fog nodes with these two commands. First command, deploy MQTT broker, and next command, fog nodes apply. And step 5, deploy neural network IDS and load prediction in the cloud layer. Create Docker image for neural network IDS. For create Docker image, use this Docker image code for neural network IDS. And for implement neural network IDS.py file to include IDS and load prediction logic using a neural network model, build and push the Docker image, and deploy the neural network model in cloud namespace with this code. And next, apply this configuration with micro-K8s kubectl apply this YAML file, neural network IDS. Step 6, enable monitoring, auto-scaling, and resource efficiency. Enable metrics server in micro-K8s to support monitoring and auto-scaling. With micro-K8s, enable these add-ons. Metrics server. For configure horizontal path autoscaler or HPA for fog nodes, use this command, autoscale deployment fog node with CPU percent options and minor max for fog nodes, and monitor resource with lens. Open lens, connect it to your micro-K8s cluster and navigate to the fog nodes and cloud namespaces. Use lens, visualize real-time CPU and memory utilization for your pods and adjust HPA settings based on observed loads. Step 7, implement neural network IDS and load prediction. Neural network IDS. Design the IDS in neural network IDS.py using a neural network trained on IoT data pattern. Trained IoT data pattern. The IDS should classify traffic as a normal or suspicious and flag anomalies. and include logging or alerting mechanism to track the IDS output the cloud layer. For load prediction, for resource allocation. For implementation, this implement a predictive model within neural network IDS.py file to forecast load on fog nodes based on incoming data. Adjust the HPA dynamically according to predictions, allowing fog nodes to scale up or down based on expected load. For deploy this model and updates with CI/CD optional. Use CI/CD pipelines to automate updates for your IoT simulator, fog nodes, or IDS models. Step 8. Testing and monitoring with Lens. For verify data flow. Ensure that IoT devices send data to the MQTT broker and that fog nodes process it. Cloud nodes should receive filtered data and run the IDS. Test IDS functionality and introduce some anomaly data into the IoT stream to test the IDS model's compatibility to detect it. Check lens logs or the cloud namespace logs to see IDS alerts. Evaluate load balancing and efficiency. For monitor kubectl top and lens to view resource utilization, adjust HPA setting if necessary to maintain energy efficiency. Load balancing. Check the lens dashboard to observe auto-scaling behavior for fog nodes and the overall efficiency of the setup. And log monitoring. Use Lens to access real-time and historical logs for each namespace and deployment, making it easier to troubleshoot and optimize. And optional things: setup, alerts, and notification. You can integrate Prometheus and Grafana tools with Lens for advanced monitoring and alerting, helping you to track of cluster health, performance metric, and IDS alerts in real time. You can implementation this scenario correctly and correctness full.